So today, I went and looked at a lot of the poster boards people had up, and people are doing a lot of very sophisticated machine learning stuff. That's not exactly what I'm talking about today, though that's a component. So as a society, we're facing a host of serious challenges. Some of them were mentioned in the prior speaker's presentation. A lot of people are under tremendous financial stress. Almost half the populations live in paycheck to paycheck. We also have many people reporting that they're not getting adequate medical care because they can't afford it. If you look at people ages 50 to 65, almost 20% of them report foregoing some sort of medical care in the prior year just due to its unaffordability. 80,000 people died of the flu last winter, and that's a vaccine preventable disease. So if we want to tackle these problems, there's kind of two things we need to do. The first is figure out who needs help, determine who it is that's likely to suffer from financial stress, or who's not getting appropriate medical care, or who's likely to die of the flu in the next season. These are questions that some of the tools that are taught in sort of the typical data science courses are kind of well equipped to tackle, this sort of predictive modeling. The second piece is the part that I think economists and social scientists can make more of a contribution on. Once you've determined who it is that is likely to suffer from whatever this adverse outcome is, you need to figure out how to prevent that from happening. And that's really a question about causality, not predictive modeling. So just to kind of frame the idea, so in predictive modeling, and I'm preaching to people who probably know more about this than I do here, but the objective is basically to predict some outcome, whether it's the death from the flu or some measure of financial stress. To do this, the typical strategy is you gather some existing data set that's got a rich set of covariates, has some good measures of the outcomes you're interested in. Then within a sample, you fit a model. Simple models that have been around for hundreds, 150 years, like ordinary least squares or logistic regression, which is almost as old, tend to work fairly well in many contexts if they're sufficiently flexibly parameterized. There's also hosts of new, more exotic models that have been developed in the last 15 or 20 years. But the basic story is the same. You predict the outcome in sample, and then you've reserved a sample, because the primary concern in this context is that you've got a good in-sample fit, but the out-of-sample fit's no good. The typical problem being overfitting rather than underfitting. But with the reserved sample, you can do a great job of determining if you've actually done well with your modeling or not. So that kind of solves the first problem of trying to target your intervention to the people that are at risk of having the bad outcome. The next challenge is the causal inference one, which is that once you know, if you want to determine what's going to happen when you apply the treatment, because you've got some person that's at risk of something and you need to figure out how you're going to prevent that from happening. And that's fundamentally a question about determining what happens if you apply the treatment versus not apply the treatment. So you never get to figure out exactly what happens to an individual because you observe the individual in either the treated or the untreated state, so you can't make the contrast. But you can compare groups of individuals that have been treated and groups of individuals that haven't been treated and see, at least on average, what the effect is. The primary concern when you're trying to do causal inference as opposed to predictive modeling is that when you're starting to compare these two groups, that there are unobserved differences between the two groups. So when you have a difference in the outcomes between the group that got the treatment and the group that didn't, part of that might be due to the treatment itself, and another substantial part of it could actually be due to these unobserved differences that you've been unable to adjust for. So when we're trying to estimate a causal effect, what we want ideally is for the treated group and the untreated group to be identical on essentially every other dimension other than the treatment dimension. When this isn't the case, we're likely to be running into problems where our treatment effect estimates are biased. So there's actually a pretty long history in economics and some other social sciences of taking a treatment effect for which we have an experimental benchmark. So we have a nice, carefully run randomized controlled trial that tells us this treatment has this effect, and then people take other data sets and try to see if they can recover that same treatment effect from these other data sets using many of the kind of modern techniques such as matching or propensity score to try to adjust for differences between the group that got the treatment and the group that didn't. And the takeaway from a host of different studies is this typically doesn't work very well. You still end up with substantially biased estimates in almost every context. For this reason, experiments are the kind of gold standard for causal inference. The basic idea in an experiment is very, very simple. You recruit a sample from the population and split it at random into a treatment group and a control group. What this does is it gives you two groups, the treatment and the control group, that are in expectation at least identical on both observable and unobservable characteristics. And that has the benefit that once you start making comparisons of outcomes between these two groups, there's only one dimension on which they differ substantially, and that's the treatment dimension. And so you can assign any difference in outcomes back to the treatment. Unfortunately, we can't always run experiments. They're sometimes unethical and they're often infeasible. I mean, some of the questions we're most interested in, such as what are the adverse effects of alcohol consumption, it's not something we can run an RCT on. We can't randomly assign people to drink heavily. It'd clearly be unethical. A vast majority of the problem with the limits of the RCT is actually feasibility. So many of the questions we're very interested in, we're interested in studying relatively rare outcomes. Take the example of the flu that was mentioned earlier. If we're interested in trying to figure out how well the flu vaccine prevents elderly people from getting very sick, we can't do an RCT to assess that. The problem is, even though 80,000 people died in the US of the flu last year, that's out of 300 plus million. So it's still a pretty rare event. So if you want to recruit a population and randomize them to control and treatment and have enough, to be powered to detect an outcome that's that rare, you need to recruit literally millions of people, and there's no way that's happening because it'd be enormously expensive, prohibitively expensive, in fact. So what do we do? The social scientists, economists, and statisticians have worked out some approaches that in some contexts actually will get us estimates we think probably have a causal interpretation even without running an experiment. The three research designs that have received a fair amount of attention in the last 30 years and some substantial developments are the kind of panel or event study. The idea in a panel or event study is basically you have a population that's all going to get treated by the end of the period you're examining, but the exact time at which they're treated is as good as random. This is the case in determination for some government programs where there's a lot of bureaucratic noise in exactly when the files get processed. So you can, with some confidence, compare people that get their determination of eligibility for the program early with those that get it somewhat later. Those groups will be balanced and you'll get an interpretation, an estimate that's got a causal interpretation. Two other approaches that have received a lot of attention in the economics and to a lesser extent in the statistics literature in the last 25 years are instrumental variables and regression discontinuity. The basic idea here is you've got, in the instrumental variables case, some sort of random variability or randomization that's given to you by nature. A good example of this is there's been a lot of studies looking at charter schools. Here in Santa Cruz, we have a charter school, Pacific Collegiate. The school is oversubscribed. There's many students that want to get in. So to allocate those rare spots, they give them out via lottery. So each year this lottery is run. That lottery can be leveraged to get a sense of exactly what the return is to attending Pacific Collegiate as opposed to going to Santa Cruz High. Because the students that get into Pacific Collegiate, there's actually at least a somewhat random component to who got in. That's the basic underlying idea with instrumental variables. Regression discontinuity, which I'm going to spend a couple minutes talking about today, is a sort of similar idea. Basically, in this case, your entry into treatment or you're probably getting treatment is at least in part determined by some other continuous variable that's got a rule set laid on top of it. An example is if you've been to the doctor recently and had your blood pressure taken, the current guidelines is if your blood pressure is above 135, you're supposed to pursue some sort of medical treatment, diuretics or something on those lines. If it's below 135, you're not. The way you'd leverage the RD idea here is you'd have people that came into the doctor and got a score of 135 on their blood pressure test and compare them with people that got a score of 134. There's a real difference in the treatment probabilities and the chance that they're on diuretics, but the difference between those two groups in baseline health is probably very, very small because on any given day your blood pressure can fluctuate a little bit. So the group that's just above the threshold could just as easily have been right below the threshold. You can almost think of it as a local experiment. I'm going to talk about the RD idea in the context of some work that some colleagues and I did about a decade ago. So the question we are targeting kind of pertains to one of those first issues we raised, which is people being unable to get care due to cost. That's something that's really hard to study using an RCT. The reason is that for many big ticket items such as elective surgeries, they're actually pretty rare. So you can't just recruit a large enough sample to run an experiment that will give you real insight into how much having insurance does or doesn't affect your ability to get certain kinds of expensive care. There's been a couple big experiments run on what the effects of health insurance are, but even the largest of the experiments only had tens of thousands of people. Whereas to look at outcomes that occur to just 4 or 5% of the population, you need multiples. You need an experiment substantially larger than that. So what we did, given the challenges in running an experiment at the right scale, was just to leverage some sharp changes in your probability of being insured. So the basic idea is that in the US, if you have 40 quarters of covered employment, when you turn 65, you become eligible for Medicare. So that lets you implement a regression discontinuity design. The basic idea is you can take existing survey data and existing administrative data and compare people that are just above or just below that threshold for qualifying for Medicare. And that's what we did using the ACS. So here is just a simple age profile produced from a publicly available national survey, and it shows that as people approach age 65, almost 10% of the population is uninsured. But right when people turn 65, they become eligible for Medicare, and the fraction uninsured drops to about 1%. And so this provides us with a simple, sharp contrast. The people that are just under 65 are very, very similar to those just over 65. What that lets us do is make a pretty clean comparison. There's no systematic differences between those two groups, and then we can overlay a second figure, which is the outcome figure. Right here in the red is the rate of elective hospitalizations, and this was generated from some administrative data that's readily available from the National Center for Health Statistics. And as you can see, the rate at which people are going in for elective hospitalizations is gently increasing in age. And then right when people turn 65, there's a sharp increase in elective hospitalizations. The only thing currently changing sharply at 65 is actually insurance status. By combining these two estimates, we can actually back out what the effect of insurance is on people's access to elective hospitalizations. And these are for like expensive surgeries and stuff like that. The same idea can be applied to examine a host of other outcomes related to health insurance. So what this gets us is a pretty high-powered way of going after even relatively rare outcomes without the enormous cost of running a humongous experiment. So just to conclude, if we want to design good public policy, there's kind of two things we need to do. The first is figure out who needs the treatment, and the second is to figure out which treatments work, and that's fundamentally a causal question. And for some of these questions that we're interested in, not all of them, mind you, but for some of them, there's ways other than experiments to get estimates with a causal interpretation that we can then use to decide which treatment we prefer to target a particular problem. That said, I'm not hugely optimistic that any of these findings will translate into actual policy changes in the current policy environment. I got a sort of amusing cartoon I found online. So this is an old cartoon, and there's a philosopher in the 1800s, and he had I can't recall the quote exactly, but some on the lines of politicians use statistics the way a drunk uses a light post. They're using it not for illumination but for support. So people cherry pick their statistics and use them as they will. So we can do all the good work in the world, but until we get the right political environment, I'm not sure we're going to see major gains on many of these dimensions. Thanks, and I'll hand it off to Rebecca.